So good afternoon, everybody. It's a pleasure to introduce to Masha Kamenetska, coming from the University of Boston University, sorry.
No worries.
Yeah, so she's actually here doing a European tour, and we are really lucky that he passed by the Basque Country to visit us. So Masha actually has been in her career in the US in big universities from MIT to Yale and to Columbia University, right? And different levels of reaching the career to professor, but now she's actually in Boston University. And she's actually doing like a big range of different topics, research topics. For example, she's going from biology to some physics and chemistry, strong in chemistry, like the things that we're going to hear today, right? So she's going to be speaking about engineering quantum properties of molecular circuits with chemistry. And this talk is being recorded, so people might be in the audience. So if anybody has a question in the audience, you can just write the question in the chat of YouTube, and then at the end of the talk, we will actually be answering them. Okay, so please, the floor is yours.
Thank you so much, Nacho. And thanks again for organizing this and inviting me. And oh, there it is. Yeah, and all the travel problems notwithstanding, I'm glad to be here. And hopefully we'll tell you something interesting about things we do at Boston University. So as Nacho mentioned, my lab is focused more broadly on single molecule spectroscopy. And so we're interested in using existing techniques as well as developing new techniques to be able to probe materials on the single molecule level. And today I'll be focusing mostly on our work with single molecule junctions, where we measure currents across single molecules trapped between two metal electrodes. So everything I'll show today was at room temperature, so not kind of different from the kind of very controlled, beautiful work that's done here, but hopefully something interesting nonetheless. And then maybe in some future talks, I'll tell you about some quantum plasmonics work we're doing, where we're actually working with plasmonic particles in liquids, and they're trapped using an optical tweezer, and we're able to read out optical response in the far field to understand charge transfer and transport properties happening between the particles. So that's another direction. And finally, we do have some projects probing molecular or biological molecules where we apply forces. So this is for example, like a piece of RNA, for example, a piece of like COVID RNA, viral genome that you can now pull and learn about its structure, stability, and so on. And this is the kind of data we get in terms of force. Okay, so if anyone's interested, please feel free to ask me about these other topics. But today I'll tell you about molecular junctions. I decided to focus on one topic, so I could go into a little bit more in depth. If you have any questions, please feel free to stop me, or maybe at the end, however works best. But just very briefly, why do these experiments at room temperature? Again, I think everyone here is familiar, but what I think is kind of remarkable and like to remind people is that even at room temperature, we have access to coherent phenomena in these junctions. So why is that? Well, because the mean free path of an electron in the metal is about tens of nanometers. And so even if you do this at room temperature, you make these junctions, on average, an electron that crosses this junction will not scatter off of phonons. And so that means you have preserved coherence. And so even at room temperature, you can have these kind of nonlinear effects in your transport that I'll tell you about today. Okay, so very briefly, how do we do our experiments? We have this modified scanning tunneling microscope where we, here's the hand-cut gold tip and a gold substrate. It's in this box. The bungees are vibration isolation, very cheap, very effective. But we form and break these quantum point contacts by smashing the tip down into contact and then pulling it out. And if we do this in solution of molecules, we form these molecular junctions because the molecules self-assemble in this gap. And again, we do this at room temperature or at 4 Kelvin. So again, very quickly, but what kinds of data do we see? So when we smash the tip down, we form a solid contact. So we have this high conductance region. And then as we stretch the tip out, we are removing gold atoms from the junction. And so our conductance, because we're in this ballistic regime where we're in this electron crosses the junction coherently, as we're removing the number of gold atoms from the junction, we're removing the number of conducting channels, and conductance goes down in integer multiples of G0. So here we have 2 atoms, 1 atom, And then the junction ruptures and conductance goes to 0. If we put molecules in our junction, we now have an additional features here. And this is kind of our molecular signature. All right, let's look a little bit in more detail at these signatures. So I've just shown you the same data again, and now we can repeat these kinds of smash and pull out thousands of times to form histograms. So wherever there's a plateau, if we add up thousands of such traces, we're going to have a peak. And so in addition to these gold signature at integer multiples of G0, which correspond to these gold junctions, we now have a molecular signature at a lower value of conductance. So again, I'm going pretty quickly. Hopefully this is fairly familiar to folks. Okay, so this is what we call 1D histogram. We can also do a 2D histogram, where now on every trace, we actually identify the sharp rupture, and we did note that as 0 on the displacement axis. And then we align all of our traces, both in conductance and in displacement. So 0 is where the G0 contact ruptures. So this is our gold signature. Here it ruptures. And then we can look and see how our molecular junctions evolve as we stretch this junction. And so this gives us an idea of how long molecules persist in the junction after this rupture point. So these are 2D histograms, and here's the 1D histogram on its side and plotted slightly different. So I'll be showing you both 2D and 1D histograms. Okay, and so now that we have a way of analyzing our data, we can start to ask questions about, okay, how does conductance of our molecules change as a function of length? And I've already told you that conductance here is ballistic. And in gold, we have these integer multiples of G0, but in molecules, the transmission probability is going to depend on the length of the molecule and on this parameter beta, which I'll show you in just a little bit. So for example, what I'm telling you is that transmission probability depends on the length of the molecule. So if we measure the conductance of molecules of different length, here's the shortest alkane molecule, medium and longest, you see that the conductance goes down. And if you plot the conductance as a function of molecule length, indeed it decays exponentially, as is predicted by this kind of simple tunneling model. So why am I telling you this? Again, just in case someone here hasn't seen this before, but also this is kind of a signature of coherence, right? So depending on the molecular family, so these are saturated, not very conducting molecules, conductance decays with a certain rate, beta, that's related to the electronic structure of the molecule. So in this case, alkanes have a large band gap, so the molecular orbital is far from Fermi, and so the decay happens quickly. Whereas in phenols, the band gap is slightly narrower, so the decay happens slightly more slowly, but it's always this exponential decay, which tells us that we do indeed have this quantum tunneling, which is a coherent process. So we can indeed see coherent effects at room temperature. Okay, so with that, so first story I'll tell you today, I'll tell you kind of 3 different stories today. And the first one is about how we can observe destructive or constructive quantum interference, but also how we can engineer it by just manipulating the structure of the molecule. So we are by no means the first to observe interference effects in molecular junctions. There's many examples. These are not at all exhaustive, but for the most part, people in the past have observed interference effects in pi-pi systems, where the molecule is really a pi conjugated system, and the electron is going to cross your junction through 2 pi orbitals, and there's going to be interference effects that are dominated by the pi structure, as well as sigma-sigma interference, where now you have saturated molecules, where all conducting channels, all molecular orbitals are really sigma in character. And as the electron crosses through these multiple molecular orbitals, you have interference between sigma channels. And what we observed is that actually you can have interference between a sigma and a pi orbital if you engineer your molecule. So this is the work of my student Hannah Skipper. And what she realized is that she looked at the kind of benzene molecule, which was not our work. This is old work done by many people, but it's very well known that if you attach linker groups to this molecule and you attach electrodes in these para positions, so this is a chemistry speak for attaching it here and here on this carbon in these ring, you're going to have constructive interference because the two frontier orbitals, I did something there. There's no, the LUMO and the HOMO are both pi dominated. And if you look here at the symmetry, this one is symmetric with respect to gold binding sites. This one is anti-symmetric with respect to gold binding sites. There's an extra phase change that you have to consider as the electron.
There's nothing there.
I'm just wondering if I press something, maybe. I don't think so. Because this, oh, it stopped working.
Let me ask perhaps it's battery.
Maybe.
Okay, I will see if yes.
That's okay. So I can use, maybe I can use the mouse. I'll use the mouse for, oh, what did I, oh,
I don't know.
your magic.
Yes.
Okay, I will try not to ruin anything again. Okay, so if you attach your electrodes this way, the electron is going to try to tunnel across this molecule. And it can tunnel through the frontier orbitals. It has the highest probability of tunneling through the frontier orbitals. LUMO is symmetric with respect to gold binding. HOMO is anti-symmetric with respect to gold binding. But now if you think about it, there's an extra phase change because you're going across a resonance. Again, I can discuss details later on, but it's very well known that this gives you constructive interference, again, because this one's symmetric, this one's anti-symmetric. Whereas if you attach in this meta position, you get destructive interference because now this one's not symmetric, this one's not symmetric, plus one more phase change, you're going to get destructive interference. Okay, this is kind of the picture that you get. So in the constructive interference case, your LUMO and HOMO add in phase and you get measurable transmission, whereas in this case, they add out of phase and you get a dip here in the transmission spectrum. So, so that's already very well established. So what happens now if you do a little bit of tweaking with the chemistry of your molecule? So now we take pyrazine, where all we've done is we've put these nitrogen atoms.
It looks like the mouse is moving also with your hand.
Yeah. Quantum effects.
Maybe it's reacting to the laser pointer also, the mouse.
I parked it far away. Oh no, now it's back. Very interesting. All right, well, let's see what happens. Nonlinear effects. All right, so now all we've done is we've put nitrogen atoms into this benzene ring. By the way, these nitrogen atoms can can bind to gold and so can anchor your molecule. I don't know why it's moving.
I have the feeling that like the laser is also moving it, but
You think this is moving the laser? I can exit. Why don't I escape? It might be worth trying again. Oh yeah, my mouse. Yeah, the mouse is moving.
alone.
Yeah. Okay. Yeah, it was just moving.
What is this?
Wow. Okay.
Oops.
Okay. Okay. All right, I'll try working.
I don't know if you
Okay.
can just take also the analog way.
All right. Okay. Maybe I'll try both. Okay, so we've okay. So what am I trying to tell you? All right, so this is if I'm okay. Okay. There we go. All right, so this is basically the very simple formula that dictates whether you have constructive or destructive interference. So this extra phase change that I seem to have been making up actually just comes from this math. So if you take two Breit-Wigner functions and then you add the two amplitudes and square them, you're going to get this interference term. And if this one is below the Fermi energy and this one's above the Fermi energy, that's going to introduce effectively an extra phase change. Okay, so when you change from a benzene to a pyrazine, you're just changing the symmetry of your orbitals. So now this one is pi and this one is sigma, but more significantly now, this one is symmetric with respect to gold binding, but this one is also symmetric. So you have a different situation from here. And so now if you think about attaching in this way, you realize you're going to get destructive quantum interference. Because of this formula, you're going to get, for this situation, you're going to have a dip at the Fermi energy. But if you attach in the other way, in the meta position, you're going to get constructive, or at least not as strongly destructive, because now they're both, the symmetry is changed. So this is kind of interesting because it suggests that just a very simple synthetic modification, you can change nonlinearly the behavior of your system. So let's test this in experiments. So what we're going to do is we're going to now measure the conductance of pyrazine alone, which can bind to gold through these pyridine nitrogen atoms. And then we're going to measure conductance of molecules that contain these pyridine nitrogen atoms, but in addition, they have an extra linker at the meta position. So now in this molecule, you have both the para channel like this and the meta channel like this. And here you only have the meta channel. Okay, so let's see what happens. So if you measure the conductance and you make the histogram, the 1D histogram in this case, you see that in the pyrazine case, you get no molecular signature. So there's the G0 peak, but there's no peak in the molecular regime, as if the molecule is not binding at all. But if you look at these ones, you know the molecule is binding through the pyridine nitrogen, because when you have this meta position open, you now have a clear molecular peak. And the fact that these two are similar suggests that they're both binding through this meta channel and giving you a conductance, whereas the para channel is acting like it's silent. Okay, so we've created a situation where we reversed the interference pattern compared to benzene. So can we do more? Oh my goodness. Forgive me a second. Can we do more? It turns out we can. So first of all, we can look at this in a little bit more detail, and we can, so this is now a DFT calculation where we can kind of test our assumptions that what's really happening is that we are having a destructive interference between the sigma HOMO and the pi LUMO. So really the bottom line here is that DFT agrees with this very simple treatment that we had before. So this is now the full DFT calculation done in FHI-Ames. And now we can also change the geometry of this junction. So, but the bottom line is that we're going to look at this most extended structure, and that's plotted in black here, because this is the structure that we most often form in our junction, where the tilted geometries has too short of a gap between the two electrodes. And so we most often form these kinds of junctions. Okay, let me turn off this movie because it can make you dizzy, and just show you that DFT predicts with this or agrees with a simple picture. So if you just look at the character of this resonance and this resonance, you see that indeed the HOMO is the sigma resonance and the LUMO is the pi resonance. And here at the Fermi energy, you have a sharp dip that is indicative of this kind of destructive interference. So you have a sigma orbital interfering with pi, and the DFT predicted geometry is very, very similar to this just very simple algebraic expression, suggesting that all the important behavior is captured just in this simple destructive interference picture. So again, DFT agrees with this picture. And the interesting thing now is that we can play with it, right? So now that we understand what's happening, we can use chemistry and modify this backbone to try to play with this basic effect. So for example, what happens if we now attach a substituent to this molecule? This is now hydroxypyrazine, this is an oxygen atom. Well, DFT predicts that now your destructive interference is a little bit diminished. So again, the pyrazine is in black, and the hydroxypyrazine is in gray. There's a little bit less destructive interference. Why does this happen? Turns out that just by putting the substituent, you reorganize the molecular orbitals. So now instead of having the sigma HOMO, your HOMO is now pi. The sigma has moved deeper down in energy, but these are now kind of somewhat degenerate. And so you actually have interference between 3 molecular orbitals. How can you tell? Well, you can just basically now approximate transmission as a sum of 3 complex wave functions that have this kind of symmetry. This one's symmetric, anti-symmetric, symmetric, and so on. And you get this green curve, which again captures what DFT predicts. So by slightly modifying this molecule, we've changed the electronic structure and we've changed the interference pattern here. We can go even further For example, now what happens if we deprotonate? We take this and we deprotonate it just by putting it into base. Well, not surprisingly, DFT predicts that we now shift our spectrum entirely. And because we've shifted our spectrum, we now predict actually quite a high conductance. So can we do this experimentally? I probably wouldn't be telling you this if we couldn't, right? So now we're going to take this hydroxypyrazine and measure it in pH 7, where it's protonated. And again, we see nothing. This is actually a pi-pi stacking feature. Take my word for it, it's not due to a single molecule in the junction. And now if we just take this sample that has this molecule deposited on it and just drop a drop of base, all of a sudden we see a completely different signature. We've turned on conductance because we've deprotonated this molecule and shifted its spectrum and in a sense turned off kind of destructive interference features. So we can go back and forth, dropping base and acid and onto the same sample and turning conductance off and on again. Okay, you might ask, why are there two peaks? Well, it's because it turns out that we can bind the molecule through this nitrogen, but we can also bind it through this deprotonated oxygen. It was a bit of a surprise to us, but we've since showed that that's indeed happening. And we get two peaks, one through the para and one through the meta binding in this molecule. But the basic idea is that we can play with these interference effects even at room temperature. So in a sense, not to be too grandiose about this, but in a sense, we've created a sort of quantum switch, which is it practical? No, but it is at room temperature, which I think is somewhat, impressive that just by putting acid and base on top of the sample, we can turn conductance off and on again with a very high ratio, on to off ratio. So hopefully this demonstrates that, we can control these nonlinear quantum effects. And this leads me to the next part of my talk, which is how we can actually, or how quantum interference helps us understand transport in these diradical molecules, which I know have been worked on here as well. Sure, if that's allowed.
Change the story.
Yes.
Like, how do I understand so when you also bind to the oxygen,
Yes.
you also can turn it on and off, but the mechanism is different than when you bind through the nitrogen, am I correct?
Yes, you're right. So the oxygen, the reason it turns off in neutral pH is because it's protonated and simply isn't binding. It only binds when it's deprotonated. And we showed that in a separate paper, which I forgot to, actually, yeah, it's right here. We showed that phenols, so this is a ring with an oxygen, have this property that you can bind with the deprotonated oxygen. That's right. So it's a totally different mechanism for why it turns off and on. Yes. Only this para peak is the quantum interference. Yeah, thanks for clarifying. Okay, any more questions before I change stories? Okay, and I should keep track of the time here.
Okay.
Okay. All right. So, so these diradical molecules I know have been of interest here as well. So hopefully this is a different perspective on these. We call them the Haley molecules. So, I showed you this slide before where I showed you that the conductance decays with length, which is a signature of quantum coherence, but it's also kind of, frustrating that by every molecule you pick up by about 2 nanometers in length, the conductance is 0. So it would be great if we could reverse this conductance decay. And as probably many of you know, recently in the literature, there's been a lot of excitement about these topological insulators, which basically are a type of polymer that you can kind of switch their behavior. In one phase, they have this wide HOMO-LUMO gap and they're insulating, indicating they will have this exponential decay. But in another phase, their HOMO-LUMO gap is much narrower, suggesting that we can have high conductance. And for example, this is the work from Pavel Jelinek showing that the same or a similar polymer, just by changing the length of the polymer, goes from kind of your typical pi structure conjugated molecule to one that has these edge states. And that's this non-trivial electronic phase with these narrow HOMO-LUMO gap. And there's, of course, a lot of, So how do we understand this? So I often give this talk to chemists, And so, in the chemistry language, these different phases can be thought of as different resonance structures. So if you just think of a linear conjugated system, you can draw it in this way where the double bond is between these two carbons. But of course, you could also switch the position of the double bond, but then you're stuck with this case where you have this edge state. And depending on which structure is more energetically favorable, this one, or if they're similar and you can have a superposition of both, you can kind of change your diradical character. So if you're fully in this state, you're in the delta equals to -1, you're the topological insulator phase. If you're completely in this kind of closed shell system, you're delta equals to +1, and often you're somewhere in between, where again, you have some superposition of these different wave functions, and so your delta can range from 1 to -1 to describe this continuum. And again, this is exciting because it suggests that if we can tune or create molecules with a lot of diradical character, then we can have narrow HOMO-LUMO gaps and a high conductance. And at the last minute, I put in that, of course, this is done many other places, including here, showing that, again, you can take a polymer from Nacho's lab and go from the kind of boring pi closed phase case to this interesting topological insulator. Okay, so in the realm of single molecule junctions, which is where my lab operates, there's also been measurements in this direction. So particularly in the lab of Lathav and Kacharaman, they showed that, for example, these cumulene molecules, which I'll show you later, maybe it's obvious to you how they're related to diradicals, these cumulene molecules show inverse conductance decay. So in other words, normal molecules decay in conductance with length, but these cumulene molecules do not. They show this modest rise in conductance. This is a cartoon, and this is the real data, but there's a modest rise in conductance here. More recently, they also showed that in charged systems, so these are now oxidized diradical cations. This has a charge of 2+, this is a charge of 1+, depending on how much oxidation you do. You also have inverse conductance decay. So for these dications or diradicals, you have to follow this top line here. And so as the molecule gets longer here, conductance, increases slightly before reverting back to this decay for longer molecules. But nevertheless, this is again promising that these diradicals can have this inverse conductance decay. Okay, but these are charged systems. These systems are charged. And so we were interested to see whether you could have something similar in non-charged systems. And so we collaborated with Mike Haley at the University of Oregon and his student Efrain Vidal, who made these molecules. And we measured the conductance of a series of these neutral acene-like molecules. To someone like me who's trained in physics, to first, if I just look at them, they seem like closed shell molecules. But it turns out that even though they're neutral, they have a lot of diradical character. So if you look at this delta value, if you remember, -1 was fully diradical, 1 was fully non-diradical or closed shell. These are intermediate. So that means, again, they have a lot of diradical character. And very recently, Nacho's group showed that similar molecules maintain their diradical character when put on gold. And so these were promising molecules for us to try in our break junction measurements. Okay, so we put these on gold and we perform break junction measurements. So just before I show you the data, just again, for those of you who are not familiar why these have diradical characters, because there's another structure, again, chemists call these resonance structure, where this kind of aromatic core is energetically favorable. And so the energy of splitting up your pair of electrons is counterbalanced by the energy gain of forming this aromatic core. And so that's why these two structures are somewhat degenerate, and you get a pretty even contribution of each to the final wave function. So that's why they have significant diradical character. Okay, so this is what the data looks like. So as you measure the conductance, I'm now showing you conductance histograms. PQ1 is the shortest, PQ3 is the longest. As you measure the conductance, it increases with length. this effect is even more pronounced at high bias. You might think, okay, maybe something is, something fishy is going on. Maybe the molecule is reacting. So we look at the 2D histogram. So here's a 2D histogram, and everything looks okay. As the molecule gets longer, the plateau gets longer as expected, and there's no kind of sharp change in the middle suggesting that there's any kind of chemical reaction happening. In other words, this really looks like the signature of these molecules, where you have this very dramatic increase in conductance as you increase the length of the molecule. So let's plot the conductance as a function of molecule length. Here we go. So if we plot just the distance between the radical centers and we plot the conductance, we see that we have this increase of orders of magnitude. So this is not just a minor increase, this is really a major increase. And if you want to capture it, many people don't like this, but if you want to think of it in inverse conductance decay, you can fit it to kind of an inverse, a growing exponential with a beta value of now negative about 1 per angstrom. Again, 1 order of magnitude per angstrom. So that's quite different from what's been explored in the past. And what's more, because these are neutral, we can very easily do IV characteristics. So now we can take one of these junctions and we can sweep the voltage as the molecule is in the junction. And again, we do this thousands of times. So what you see in the color map in the background is thousands of junctions added on top of each other, where we trap a molecule, sweep the bias. And white is now the average behavior. Okay, so this is the shortest, middle, and longest molecule. White is the average behavior. And in dashed lines, I plotted linear IV curves that would indicate kind of, very boring situation, closed shell character where there's no resonances within the bias window. And clearly what we see here are superlinear behavior, right? So initially this begins kind of linearly, but then it shoots up, the current shoots up, indicating that we're approaching our molecular resonances in these molecules. So in other words, that there is a small HOMO-LUMO gap, and that the HOMO-LUMO gap is decreasing as you make the molecules longer. Okay, let me just summarize this. I will convert these current versus voltage curves into the conductance parameter that's very common in this field. I know, again, some people don't like plotting conductance versus voltage, but that's the convention. So that's what I've done here. So again, the shortest molecule has the widest HOMO-LUMO gap, which decreases with length. But what's most remarkable is that you have this dramatic increase at all voltage values. Conductance increases even at 0 voltage. And, we called it extreme anti-ohmic behavior. It seemed, as far as we know, this is the highest increase with length that's been observed so far. Okay, so why is this happening? So again, this is probably familiar to most of you, but in linear chains, this kind of phenomenon is often modeled by 1D SSH model or tight binding model, where again, we can model where we put this double bond to model the transition from this closed shell system to the open shell system. So if T1, which is the hopping probability, is greater than T2, then the double bond can be said to be between these 2 carbon atoms. And if you parameterize it in terms of delta, then when delta is greater than 0, T1 is greater than T2, and you get the closed shell system. Whereas when delta is less than 0, T1 is less than T2, and you get this fully open shell system. And in between, you have a continuum, a delta equals to 0. For example, you get a kind of fully metallic state. So using this parameterization, then you can write down this tight binding Hamiltonian, and you can solve it pretty easily as a function of delta, right? So at delta equals to 1, you have the boring wide band gap situation, insulator, but as you decrease delta, you close the gap, and in this diradical state, you have no gap. And this, again, is very well known. And so this is a useful model. It seems to predict this kind of closing band gap behavior, and perhaps it predicts higher conductance. So let's test whether that's the case. Let's now take this Hamiltonian and calculate the transmission of this system. Okay, there I've just extrapolated for all values of delta. And now I'm going to look at the transmission. So in the closed shell system, you have low transmission because you have a wide band gap. In the middle situation, the metallic case, you now have a lower band gap, so you have higher transmission. And in this fully diradical situation, you have no band gap. And so you might think, aha, this is the situation I actually want. I have no band gap here. No matter how long my molecule becomes, I will always have high conductance. But it turns out that this is a topological state, right? So there's high density at the edges, but it's still an insulator in the middle here. And so even though you have a resonance, this is the model prediction, as you make the molecule longer, your conductance still decays exponentially. This is not what we see in our molecule, right? In our molecule, we see that conductance increases with length, whereas this predicts decay with length. So what's going on? So let's take a look whether intermediate diradicals, so not these full diradicals, but intermediate diradicals, which is what we have in experiment, can actually do better. So we're going to focus on kind of this intermediate case, and we're going to stick with this model system, which is this single chain, for just another few slides. And what we're going to do now is we're going to reparameterize it with real parameters from experiment. We're going to look up the value of T1 and T2 from experiment to predict the conductance. So if we focus on this chain and pick delta equal to 0, which is that metallic case, and use these real numbers from experiment, this is what we predict. These are now the enes, and we predict with our model that as you make them longer now, actually transmission at 0 should stay unchanged. It remains the same. Why am I showing you this? Well, because I've showed you previously that there's actually experimental measurements for cumulene, which I would argue is a good kind of real world analog to this metallic state. And if you remember what they saw there is that conductance, okay, increases, but very, very slightly. In other words, the experimental finding is in pretty good agreement with this model, saying that in this kind of linear system, at delta equal to 0, so in this metallic intermediate state, as you make the molecule longer, conductance remains pretty flat. Okay, what about our system? Okay, one last thing I forgot to say. How can this happen? You're closing the band gap, but the conductance remains unchanged. So you're bringing the molecular resonances closer to Fermi, but the conductance doesn't increase. And I would argue the only way that can happen is that you have some sort of interference effects. You have more molecular orbitals close to the Fermi, in the Fermi window. They're interfering with each other such that any gain from the closing of the band gap is being canceled somehow by destructive quantum interference. And in fact, you can look at that. You can take the model and you can break contribution to transmission into constructive CQI and destructive DQI contributions. And you see that delta equal to 0, which corresponds to this experimental case, they basically cancel each other out. And so you make the band gap smaller here as you make the molecule smaller, but you get no gain in conductance. Okay, so that's in the system that's been done before. What about these kind of polycyclic molecules? Here you have to just modify the parameterization a little bit. And this was the work by my student, Brent Lawson, where now you have to worry about these other bonds. And it's actually very simple. If you just parameterize them like this, it seems to work out, right? So now we have a model for our type of molecule for this polyacene or these acene-like pores. And we can do the same kind of a tight binding Hamiltonian and solve it as a function of delta. And so again, we see this wide band gap at delta equals to 1 and narrow and no band gap at delta equals to -1. And here in the middle, delta equals to 0, we're going to take this as an approximation for our intermediate diradical molecules. And again, we see this shrinking gap with molecular length as we expect. Okay, so now what does our model predict for transmission? This is kind of the make it or break it moment. This is the predicted transmission. And if we look at the Fermi energy, we now see that here at 0, instead of staying the same, transmission increases or is predicted to increase as the molecules get longer. And this is exactly what we see in experiment. And interestingly, right, this is, again, just to remind you, let me just remind you what we saw in the acing case, very different from what we saw in the linear chain case, polyene case, where conductance didn't increase because the destructive and constructive interference cancel each other. Here, if we break down the transmission into constructive and destructive components, we see that the constructive interference component always dominates the destructive interference. And so the band gap closes, and concomitantly, we have an increase in conductance, just like we saw in experiment. So part of what surprises me is that this simple model, and this is what I asked Thomas, seems to at least capture the behavior we see in experiment. And what's more is that it predicts, so now I can plot the transmission predicted as a function of delta. So the red marks the molecules that we have of 3 lengths, right? These are the 3 lengths, and these are the diradical character. And if we can increase diradical character through chemistry, for example, by modifying the molecules a little bit, we predict an even greater transmission, an even greater inverse conductance decay. So can we do this? Well, chemists are sort of like magicians. They can make these materials. So Michael Haley and his team synthesized a set of 2 other molecules. So now these 2 molecules, they have the very similar structure to the BQ1, BQ2, BQ3, but now they have this thiophene addition on the ends. So everything else is the same. This binding linker is the same. The core is the same. The radical center is here at this position. But now in addition, there's this thiophene, which increases the diradical character. So for example, BQ1 is the same length as this anti-IDBT, but it has different diradical character. And if we look at the conductance, then we see comparing BQ1 to this pale green molecule, we see that the conductance is increased. And same now for this double, the 2, compared to BQ2. Again, we see a dramatic increase in conductance from this medium purple to this medium green. So same length, but now by chemically engineering the molecule, modifying it a little bit, adding some diradical character, we can kind of tune the conductance properties and even increase this inverse conductance decay that we saw before. Okay, I went through that pretty fast. I have one more short story if I'm allowed, but I'll pause to see if there are any questions before I shift gears a little bit.
I have questions, but perhaps we can do that at the end,
Finish,
right?
okay.
Yeah. And then somebody has some questions now. Okay, let's go to one, and then we can have some small discussion.
So the last story is really, I know that I should be finishing very soon. I just wanted to very briefly show you this kind of our recent work and how we can form structures in situ in the junction that aren't really accessible synthetically. In other words, these structures, you can't really make them in bulk and then introduce them into the junction. Instead, you assemble them in the junction. And so they're kind of a new or a different group of materials that are only accessible in this way. And maybe they're interesting for probing in vacuum or at low temperature. So just, this is just a motivational slide. This is obviously not our work. But for example, the group of Wernsdorfer is interested in using metal-containing molecules and many other people because a metal-containing molecules has a lot of degrees of freedom, including spin. And so you can imagine using them for people have proposed you can use them for quantum information science or to make certain kinds of switches. So this is an attractive molecule to put between 2 metal electrodes, and people are doing it. But it's actually quite challenging. In other words, when you try to do this, your error rate is very high. Very often you don't form this kind of junction. And part of the reason is that we, as well as Richard Burnt and others, have showed that actually a metal-containing structure is unstable in the junction. And fundamentally, it's because if you think about a molecule that has a metal center, you realize that the strength of the bond between this metal and this linker is similar to this bond between this gold electrode and the linker. And so if you try to put it in the junction, the interaction strength here and here is the same. And so you're very likely to break it somewhere in the middle, even if you're not pulling, just, thermodynamically, you're very likely to break and have the linker bind to gold instead. And so again, this is not just us, but others have seen this as well in STM at low temperature. And so it can be actually quite challenging to assemble metal containing molecules in the junction. So we kind of came up with some chemistry rules. I don't want to go into too much detail, but basically how to pick these linkers to make this more robust and more resistant to break down. And so after forming these rules, we started thinking about what kinds of molecules actually could be robust enough to withstand our junction environment. And so Hannah Skipper, my student, found that cyanides actually tend to form these complexes with gold in the solid state. And so she proposed that perhaps we could put this ion in the junction and form a stable junction. And there's kind of chemistry reasons for why this should be more robust. Basically, this bonds to gold both through the sigma bond and also through this pi back bonding, the chemists call it. But in any case, she put this molecule in the junction. It's a salt. And indeed, she sees these very robust signatures due to this molecule. So, we spent a long time trying to understand why there's so many signatures with just this one single molecule in the junction. And, it turns out, this is the 2D histogram, it really looks like what you're forming is getting longer as you keep stretching it. So these plateaus are longer than these ones, as if you're building up a chain. And so we did a lot of analysis to show that that's exactly what's happening. So you can kind of group these into 3 groups, and you can show that the shortest group, is about 0.5 nanometer shorter than the medium group, which is about 0.5 nanometer shorter than the long group. So again, you're adding 0.5 nanometer of molecule as you stretch this junction apart. So what can this be? Well, you can look at the conductance of these different peaks and how they decay. If you assume that you're adding some sort of unit, how do they decay? And you can see that they decay exponentially as if indeed you're building up this chain. Long story short, what we think is happening is that you go from like the single cyano unit to the 2 cyano units to the 3 cyano units in the junction. And again, these are now modeled in DFT. And indeed, the binding energy is high. This is per bond. And so this is a stable structure. And the predicted DFT conductance, this is now the transmission curves, matches well with experiment within the kind of expected area of DFT. And so, there's many interesting things here. For example, different structures give similar conductances. But what I want to focus on is that you're, again, assembling this chain, which is not accessible synthetically, or you can make a solid state structure of it. But here we have like a single chain. And this could be interesting, but these are charged. These are actually salts. And so they're challenging to work with in some respects. We're still continuing studying transmission through these. Just one side note is that the conductance decay here is actually similar to an alkane. So it's actually quite an insulating structure, even though it has all these metal atoms in it. But the bottom line is, again, let me just skip this in the interest of time, is that we're forming these chains. And there's another example from our group, which actually is from earlier, that we can form chains also with imidazolate, again, a charged linker. And then most recently, we showed that actually neutral linkers, so related to these imidazolates, but now they're neutral, also form these structures, these chains, elongated chains. And so, perhaps this is something interesting that you can study in vacuum. There's a lot of evidence that you can replace this metal atom with maybe another metal. It doesn't have to be gold. In our case, it's gold. But if you do this on silver, then perhaps you incorporate silver and so on. And so this is kind of an interesting approach to creating structures in your junction that aren't accessible otherwise. Okay, so that's all I wanted to say. I want to leave plenty of time for questions. And I just wanted to acknowledge my group. This is my group. And I've pointed out the people who did the work, Brent, Hannah, Shayun, and Zelen. And thank you again for your attention. I'm happy to answer any questions, and hopefully we can continue this discussion going forward. Thanks so much.
Thank you very much, Masha. Very nice. So the people, if somebody is in online, you can just write the question there, but we can start also for some question here in the meantime. Daniel?
Thanks, Masha, for the nice talk. I have a very naive question from physics point of view. On the last part of your talk, when you were showing these chains with gold atoms in between, like if I was not mistaken, you have shown your slides that the fundamental unit is like nitrogen, carbon, gold, and then mirror symmetric. But then when you make it longer, how do you think this is breaking apart? Because it seems like it's breaking apart. How do you think this happens? And then it forms like a longer chain, because then the unit that is repeating is shorter, right?
Yeah, so you're saying how can we go from the full molecule, which has two cyano units,
Yes,
to kind of the monocyano.
Exactly.
So, this is not actually a physics question. Actually, the chemist asked me the same question. So I don't think I have a very good answer, except that we've tried to account for this, what we see, by assuming that the full molecule is the unit, and it doesn't work. DFT doesn't agree, the lengths don't agree. It really seems like we have these single cyano units. We also tried in DFT to bind it and then see what is the energy to break the molecule apart. And it's very high. So I don't have a good answer. I know I could make an argument that thermodynamically, even though the energy is so high, you have so many of these on your surface, some small fraction will break. But in addition to that, we have to remember we have high electric field. So we have a pretty high field across the junction, and we also have force. So we're pulling it apart. So even though at zero force and zero field, the probability of it breaking is low, given that we're pulling it on the gold surface, which is reactive, that's the other thing. Unlike vacuum, our gold surface is not gold 111. It's this somewhat reactive corrugated gold. So all of these things combine to kind of reorganize these bonds.
Like that's the fact that the fundamental monomer is charged, maybe that also matters. I was thinking, because I was trying to replicate this in my mind, but I didn't know how to do it.
But probably it's charged, right? Because this is a very known anionic unit, right? So
the cyano, gold cyano is charged. Actually, if you take off one of the cyano units, it becomes neutral. But that depends on the oxidation state of gold, which is a little hard to assess when you're on the surface, because the charge, there's an infinite source of charge on the electrode. So I don't know if I'm answering your question, but it's unclear, but it's very clearly what we see. And that's partly why it's not published yet, because we spend a lot of time trying to make it convincing that we are really reorganizing these bonds, but
Is another question? Yeah. First. Yes.
Your comment when looking at the cyano groups is that you need strong bonds to be connected. You tried looking at cage-like molecules that could catch a metal but still retain those bonds around the metal?
We're actually working with a group at MIT who makes cages. But is your thought, can you say again what your thought is, that those bonds will be more robust?
So the cage-like molecules I've worked with will bind metal centers, but they have covalent bonds looping around the metal. So you pull and you'd still have covalent bonds holding everything together.
I'd love to hear more about these, because at least from my understanding, most cages actually rely on these coordination bonds, again, often between like a pyridine nitrogen and the metal center. And those in our experiments are not robust. You put them on our surface and they rearrange, and then the pyridine nitrogen binds to gold instead. But I'd love to hear, maybe there's some stronger bonds that.
Okay, I'll show you a cryptand molecule.
Okay, great, thanks.
I mean,
You had the project where you showed that the conductance is increasing with the length, and the origin seemed to be that the resonance was shifting across Fermi. If I understand the graph correctly, so you could imagine that if you were to make it, there would be a maximum if you further increase, and then the conductance should go down again. That's at least how I would interpret the graph. Have you tried to look in that direction?
So actually, our interpretation is not that we're shifting a resonance across Fermi. Okay, here, in this model, the resonance is predicted to approach Fermi, but it never crosses.
Okay.
We know that because if you look at conductance, the conductance is still far below 1. Also, this is a prediction, so you can't really take very seriously the exact alignment here, right? The point is that anywhere you look here, so even if this predicted alignment, so for example, DFT is well known to mistake the exact alignment, but anywhere in this intergap region, conductance increases with length, in contrast to this situation where that's not true. So does that answer your question? So it's not that it crosses across Fermi. It's that
approaches.
it approaches, but more importantly, somehow there's no destructive interference effects that push this conductance below the pale conductance, if I'm making.
Okay.
So here, no matter you close the band gap, but conductance doesn't care. In most molecules, you close the band gap and conductance decreases, right? That's most molecules. Even though you're closing the band gap, conductance decreases with length because there's destructive interference. In this case, you have the reverse situation. You close the band gap and conductance increases.
If I may ask, there is a parameter also that actually in this simulation is not included, which
Yes.
is a charge transfer. So in principle, the system doesn't have to be particle hole symmetric like you put it there, but it could be. Do you actually get some fingerprint from charge transfer in your junctions? Because in the
Can you say a bit more? What charge transfer between the metal and the molecule?
yes, it's actually you are partially, perhaps it doesn't have to be that you are transferring one full electron, but somehow electrostatically the LUMO or the HOMO can be shifting.
So we actually think so I don't have so we think, oops. Let me try, okay. The Q&A is open, so let me just scroll back, maybe. Maybe I can scroll back. Yes. So you can see that, I think, if you look at the 2D.
Mhm.
So we think that that's why let me go forward. Here, we're really on top, for this longest molecule, we think that at this bias, we're really on top of the resonance. We cut it off here because what happens next is it plateaus, and then actually we do some chemistry. It jumps and becomes unstable.
Okay.
And we think it plateaus not at resonance because there's a charging and we can no longer apply this very simple one electron model.
Okay.
So we see that when we really go close to resonance, we see charging.
But overall, everything is quite symmetric, I see always.
Yes.
Right?
Yeah, and we've tried, it's not sensitive to how you apply the bias.
Have you tried to use another metal, like
Sorry?
gold? Another metal, not gold, but silver, for example? How is it possible?
So yeah, it's because we're in air. It's always a challenge, but yeah, you think that because we just changed the work function.
So the silver gets more oxidized, right? So it's more
Right.
difficult to work with it.
Yeah.
Okay.
But yeah, it's something
Yes.
we could try. Yeah.
Good. Is there any other question? Okay. If this is not the case, I think in the audience it was.
No, I don't see anything.
I don't see any. It was Andres over there, but or Andres. Okay. So thank you very much,
Thank
Masha. It
you.
was great having you here and
Thanks.
beautiful results. Yeah. The Halley molecule is
Yeah,
beautiful.
It is,
Yeah.
yeah. So that's why I thought it might be of interest.
Usually, actually, the platform usually
Yes.
Why so actually?
It's actually consistent with the length because we have to remember we have the linkers at the end. So